of controllers and so forth, and we'll go from there. So I want to highlight the most common motors that we use, guys, in the electrical industry and the best way of controlling them. How many of you guys have read the chapter? Anybody read the chapter? I know you read the chapter. If you read the chapter, you really associate with it. A couple of things, guys, that we're going to highlight in this. I keep throwing all these machines here for you. You can see all these machines. All these machines are driven by motors. So the chapter keep track of the machines in the industrial project, the machine layout and the motor that driving these machines. So because we are following a book, there's machines and driven by the motor. So all the motors inside this project, we'll talk about the description, how they work and so forth. Types of motors and motor controllers is a couple of things very important, guys, from a magnetic starter on the wall all the way to VFD and so forth. And branch circuit, motor branch circuits, installation. We did extensive calculation in branch circuits and feeder calculation motors. So these are the few things I want to go. If you don't understand, this is one of the most important formula that you guys have. You have them also in DeWalt. All these formulas about motors are in DeWalt. Tons of, I think, very, very important. If you guys go to page 1-4 in DeWalt, all these formulas are there. This is one of the most important formula that you're gonna find, based on the horsepower press and the power factor and the efficiency. I can find the full load amp of a motor. The full load amp of a motor. This full load amp. This is full load amp name plate. You remember, guys, when it comes to motors have two full load amps. One the code and one the nameplate. This is how they calculate the nameplate. This is what you calculate right here is the nameplate. So if I give you an efficiency of a motor and a power factor and a horsepower and a voltage, of course, a voltage, you have to have a voltage. You can find the full load amp. With this, I want you guys. I always highlight one little very important thing. Chris, and I'm not going to talk about Chris, but what happened if the efficiency goes down? What happened to the full load amp? Goes up. Do you see how the efficiency of the motor is very important? The current goes up. Bad news. Take this again. What happened if the power factor goes down? What happens if the power factor goes down? The full load amp goes up. Does it make sense? Who cares? The question is, who cares? Every time you have a low power factor, remember we said if you have a low power factor, you have high current. Bad news. If you have a low efficiency, you have high current. Bad news. Bad news. Meaning more current going through the conductor to do the same amount of work. The same amount of work. So these are the only thing I want to highlight. What happened if you reduce, if the efficiency of the power factor goes down? So what does that tell you, Rob? Tell you always use efficient motors, always use power factor correction to correct your power factor to as close to 96% as possible. Later on, Chris, you already did the capacitor chapter. That's why they go to the capacitor and correct power factor for motors, because of that thing, to reduce the full load amp. And of course, if you have your choice, this is a design choice. This is a design choice. If you have a choice, always go for higher voltage, always. But that's a design. If you have your choice, guys, when you go to a building and they tell you what voltage system do you want, always choose 48277 in the US. So always use a higher voltage that you can utilize. Any question, guys, about this formula?
Is that the same one that code uses to drive their FLA?
The code uses, very good point. The full load amp in NEC code book, guys, it's because of the efficiency and because of the power factor are unknown. So the smarter than Chad decided to say, and because of the voltage also fluctuates. What happened, by the way? Take this. I'll answer your question. But I have a 480, right? My nominal voltage 480. Chris, what happened if I have a voltage drop situation and my voltage went to 450? What happened to the current? Goes up. Because of all these factors, the efficiency, the power factor, the voltage fluctuation, the NEC code book take a very conservative approach and take the worst scenario and give you a full load amp. If you go to the NEC code book, if the nameplate, guys, of a motor, on a motor, it says, say, 90 amps, for the same motor, the same voltage, if you go to the book, you're guaranteed you get probably 10 to, I would say, 15% extra on it. 10 to 15% extra to accommodate for all these factors. So
Is it a PAT formula though, or is it just all
I don't know. I haven't figured that out. See if Excel can come up. But I would, from my just running certain numbers, Chris, I would say 10 to 15, maybe 20 extra. So what's 10% extra on 90? That will be, what's 0.9, right? 10% or say 15. So then maybe the full load amp even get, so let's just say 91 amp. Is that 10% of 90? Or no, 99, Chad.
Yeah.
90, what am I? 1K today? Anybody have me some money? Did you put anything in the coffee, Chris? 99. Nick, did you put anything in the coffee today? So, so you'll find 9 extra amps because you don't know which manufacturer guys make the motors. So in the NEC code book, table, Chris, what was it? Table 4, 30.250, right? For the 3-phase, will get you up it a little bit, 10 to 20, 10 to 15%. Cool? Just because when I start designing, I have no idea which motor am I going to end up with. Any questions guys about this formula? So for the most part, that's why we use the NEC code book. Then we don't have to mess around with the system. Now, if you're managing a plant, guys, knowing that your power factor is down is a big deal. But if I can get you to understand, improving the power factor and the efficiency and having a good voltage, no voltage drop, will improve the full load current. Everybody got that one? That's all I want to get. That's why we always keep hammering guys into low voltage drop. We don't want a lot of voltage drop. We want the efficiency of the motor to be good, and we want the power factor correction, like we're going to do in the coming chapter. Okay, these are just a couple of types of symbols that they guys use. You're familiar with them. We'll talk about diodes and SCRs, guys, in a second, but review these. DC motors, probably you're not. I don't know how much familiar you are with it. We'll talk about this one in a second. The rest of them, you should be familiar with these. The single most important motor that you're going to encounter in the industry, in the construction industry, guys, is called the induction motor. That's the single most, or squirrel cage induction motor. Squirrel cage induction motor. The cheapest, easiest way of making a motor is an induction squirrel cage induction motor. And you guys are very familiar with this. We have them in our lab. What they do is they have bars over here, the rotor, shorted bars. They have bearings over here, you can see mounted on the bearings, and they rotate inside a coil. The cheapest, easiest way of making it. Why it's important, one of the most important thing about these, and then you have your wires, the 3-phase wiring here, bringing you 3-phase. Low maintenance, nothing. There's no coils. It's a chunk of metal inside a coil, and it rotates because of magnetic field. So that's the cheapest motor they're going to get. You are familiar with, by the way, motors, guys, you're going to have induction motors, you're going to have synchronous motors, and you're going to have DC motors. These are the most superior motors in the power industry. So all the air handling unit that you have, rooftop units, they're going to have some type of an induction motor. Any question, guys, about the shaft tied to the rotor, so-called the rotor here? And that's where you tie your fans and all this good stuff here. And then in this area, you get your 480 system or whatever voltage. Any comments, guys, about this? How the construction, I know we studied this in the past, but that's the most important. Chunk of metal inside a coil rotating. So that's the most important thing about this. They can have aluminum bars or copper bars, aluminum bars, shorted at the end. 1, 2, 3, 4, bam, bam. Shorted at the end. The good thing, I don't want to make it motor class, guys, because there's a lot about motors. The single most important thing is when we talk to the mechanical engineers, when it comes to motors, is the starting torque and the running torque of a motor. Electrically speaking, we care about the starting torque and running torque, not amp, torque on a motor. But the mechanical guys everything that they do is based on the torque. How much torque you can get out of this motor is a big deal. It gives you the ability of mechanically, physically doing a work. So these guys have good starting torque. When you have high starting torque, sometimes you have high inrush current. That's bad news. So you have to kind of balance between the starting torque, a high starting torque, and low starting current. And they design them in so many shapes and forms, guys, to kind of try to find the balance between high starting torque and high inrush current. Common magnetic. So what they do, guys, they have a magnetic field between the two of them. If you're familiar with the way they work, these guys work. You bring power into the coils right in here. You create a magnetic field, right? Every time you put AC current or a DC current in a wire, you create a magnetic field. The magnetic field of the stator induce. Induction is like love. You can't explain it. It just, you can feel it. Oops. So you can induce into that rotor. You induce a magnetic field on the rotor, guys, and induce voltage. As a matter of fact, you induce voltage, and because induce voltage into the rotor, and because the rotor is shorted at both ends, when you induce voltage, what do? And you have a voltage across a wire. What do you get? And it's shorted. You get a current. So you induce voltage in here. So here's my voltage came across here. It's shorted at the end. So what are you going to get? You're going to get current, induced current. Now that baby induced current, when you have a current in the rotor, it's going to create a magnetic field. We already have a magnetic field in the stator because of the voltage. The magnetic field of the rotor and the magnetic field of the stator interact with each other to get you the spinning, that magic that's called spinning. It's really the principle of operation for almost all motors, not just this one. The induction, magnetic interaction, when it's as easy as putting north next to the north or south next to south. They pull away from each other. So that's the common principle. That's where the word induction. You induce a voltage from the stator into the rotor. The induced voltage creating an induced current. The induced current create a magnetic field. The induced magnetic field interact with the original magnetic field that comes from the voltage. Interact means you have a north and a south next to a north and a north next to each other. They pull away from each other. Here's one pole, then it keeps chasing. Then you have a rotating magnetic field because of the AC, guys. The north keep moving and the other north keep moving away from it. So if you can imagine a magnetic field rotating because of the AC, and the rotor magnetic field also is trying to chase that. So that one is moving and the other one is chasing it. Long story short, that's what you get, the effect of spinning. So, and I know I'm not gonna focus too much on the basics. Any question, guys? But you have to understand the whole concept is induction. Yes, sir.
Have you heard of that Dyson motor, the digital one? Is there any feature of that?
I heard about it. I don't know. I really don't know. Yeah. Motors, guys. We have shops. We have shops that specialize in motors. I mean, there's so many ways of getting. There's so many. It's a specialty by itself. So put it this way. There's so many small motors for control, blah, blah, blah. The most important thing for us, at least in this industry, the construction industry, is these induction, the horse motors, the induction motors. As of now, these are what you're going to encounter in air handling unit, chillers, and so forth. Okay, this is for your friends, the mechanical engineers, and for us guys. One of the most important thing that a motor can do, if you were to define a motor, Nick, in 2 words, you're going to say it, okay. 1 word, 2 words. It's a machine converts electrical to mechanical. How many words are these? Or mechanical energy is coming from electrical energy. You have electrical energy in here, you have mechanical energy in the other side. What's mechanical energy? I can drive a bus with it. I can run an air handling unit. I can cut. So that's really the most important thing in terms of motors. That's why they are superior. Because I can replace 15 Chris's with 1 machine. Instead of cutting wood, Chris will sit for 1 day cutting wood. I can replace it with a saw, and he can cut it in 1/100th of the time. Okay, so this concept, guys, is very important. This concept gives you the torque. How much torque can you get out of a motor is proportional to the horsepower and the RPM. Can you guys see the higher RPM based on this rule? What happens if the RPM goes up, Chris, here? Based on this rule, the RPM goes up, that guy goes down, the torque goes down. What happens if the horsepower goes up? The horsepower goes up, well, you get how much torque? Get more torque. It makes sense. If you want a more mechanical work done, what do? A bigger motor, a bigger fat horsepower motor. So this concept is very, very important, guys. That's where you can convert torque into horsepower. The mechanical engineers next, they take the torque and then they log it into their own formulas so they can size all their mechanical equipment based on the torque that you have. So this one is the link between mechanical engineering and electrical engineering. The link between us. Or if you, as an electrical engineer, you take your torque, how much torque do you want to pull this process? And you size the horsepower to get you that particular torque. So can I get you to understand that this formula is very, very important, guys, for designing machines? Okay, so that's my my spinning. This slide, guys, give you, Chris, all these M's and MCs and MVs here. All these M's and MCs and MVs, they are listed in industry. We have an industrial project, and they're giving you all the horsepowers and also number of motors you have in each one of them, and what are they cooking, and number of machines, as well as the assigned number for them, So we have number of motors in the machine. So most like this, I have 6 machines here, and 18 motors. So it must be 18 divided by 3. So each machine has 3 motors in it.
Is that code just apply to the printer, or is that something in the industry?
To apply what?
Like, what is the meaning of the code number outside of?
No, this is really the code number.
It's a tag.
It's a tag. Really, yeah, I know code to us is NEC code book. This is just the tag that they're putting inside the plant, not the NEC code book. No, not that I know of. And also here the horsepowers. Alaribo, can I get you to understand that some machines, look at this machine here, each one of them has 3 horsepowers, 3 motors. So we always think a machine is a horsepower. Some machines have multiple horsepowers or multiple motors running them. Any question guys about these? And look at all of them are what? What type? Squirrel cage induction motor. To sound intelligent, if anybody asks you what type of motor should we use for this process, 3-phase induction motor squirrel cage. Done. Any question guys about this? So these are all the machines that we have. And then they have some industrial plant at the top, some HVAC equipment that they're adding different number of motors in each one of these machines. For example, they have a ventilation blower, 6 ventilation blowers, each one of them on the roof. They have a 3 horsepower motor, blah, blah, blah. So they have air conditioning equipment also, have this amount of horsepower, 6 of them. So these are called HVAC. These are the HVAC equipment, not the owner, not the owner equipment, the HVAC equipment, the HVAC. There are 2 types of motors in this plant and our plant, guys. Ones that drive the heating, cooling, and ventilation system, and ones that drive the process, make things. Any question, guys, about these? All of them induction motor. All of them are induction motor. Okay. Sometimes we need, so we know that induction motors are great, guys, but there are 2, so we decided the induction motor. The second thing that you have to decide is speed control for motors. The cheapest, easiest way of running a motor is turning on and off, full speed on and off, full speed on and off. That's what we ran most of the stuff. The next step is, what if I want to run a motor on multiple speeds? So there's multiple ways of doing multiple speed. This guy is a 4-speed motor. I'll show you the induction. So you have to get you different speeds for induction motor. They used to, Chris, to have, well, I'm sure they still, for certain industries, they have multiple windings. So they have certain windings. We give you certain windings, guys. They energize one set. Here's 3 windings here and another 3 windings here. If they want 1600 RPM, they will energize only these windings. They don't energize this. If they want an 800 RPM, they energize both of them. So they have multiple windings to energize to get you different speeds. We'll look at these in a second. So to change the speed, what they do is they do the number of poles. They change the number of poles of a motor. Number of poles of a motor. So and these are they do them by the windings. The windings, guys, will reduce half. Will get you half of the speed. So if it's at 1800 RPM, you will get 900 RPM, and so forth. With the VFDs, you can get almost any speed you want right now. But that's the old way of doing it, having multiple motors at different speeds. With this one, I want to show you. So we got that one. I want to show you guys that motor here, since we're in it. We got these. Okay, got the controller. Then we get into the motor itself. Speed control. Where the heck is that going now? Okay, well, we'll get to it when we get into the pictures. But it really did, we energize different windings to get you different speeds, different windings to get you different speeds. So that's getting different speeds. The other thing, guys, is starting a motor. When you start a motor, the worst thing for starting a motor is the air rush. What's wrong with the air rush? Two things wrong with the air rush. We always call it, guys, electrical stress and mechanical stress. Electrical stress means you have a voltage drop. When you start the motors, the light will dim because huge amount of current got sucked by multiple motors. Your light will dim. So that's bad. That's electrical stress in your system. High voltage drop as you start the motors. Certain motors might not start. If you have 50 motors starting at the same time, you wouldn't have enough voltage to start all of them. So electrical stress. The second thing is mechanical stress. High starting torque, high starting current will create a high starting torque for you. So imagine if you want to start something and it jerks it, right? You want to smoothly move something on a conveyor, and instead of smoothly moving it, it's jerking it. When you start, it pulls that conveyor and things will fly all over. Because of all of this, guys, they want to reduce the starting current, to reduce the starting torque. Here's one method of reducing the starting. So this is all to reduce the starting current. This is the I start. Remember that I start? If I run, guys, on a motor is 10 amps, I start is usually, say, let's just say 6 times this. 6 times 10, that'll get you 60 amps. For only what? 10 seconds. Only for close to 10 seconds. That's all. Not a whole lot of time. 6 to 10 seconds, you will suck 60 amps to start to run a 10 amp motor. Who cares? Stress, mechanical stress, electrical stress. The Smarter Than Chad came up with a couple of old methods, they call them. This system, guys, when they start, without getting into all the, when you push the button to start, you energize this coil, you close this contact, bam, bam, bam. Now the current, guys, goes over here through the resistor into the motor, and I'm going to just track one current. If the voltage here is 480, you will lose, I'm just going to lose 200 volt across this resistor, so that will give me a voltage of what? 280. So I started my motor at 280. I reduced the voltage momentarily. So by reducing the voltage, remember that formula that we were looking at? When I reduce the voltage, what happened to the current? Psst, goes down. That reduces the air rush. Okay, so for 10 seconds, then you have a timer. See that timer here? After 10 seconds, this baby closes, right? When this timer closes, guys, that's what happened. Let's use a different color. After 10 seconds, that will close, then energize the run, and then bam, bam, and bam. What happened if you put a conductor across a resistor? You shunt it. So now the current is going, instead, it's going to go right here, back here, and your 480 here will translate to what? 480 here. So they call it voltage reduction. You reduce the air rush by reducing the voltage. Now with VFDs, they do it with VFDs, you reduce it with VFDs, the frequency and the voltage. So that's one method of reducing air rush. Who cares? Remember that 60 amps now? If I do it this way, I can cut this one almost to 30 amps air rush. That's better than 60. One progress. Any question, guys, about this? They call it primary resistance to reduce the voltage. If you guys, I don't know if you did it with Gary, guys, in our labs, we have multiple motors that we wire here. The second one that does the same thing, Chris, is in auto transformer. The same principle. You push the button here, you energize this coil, right? So you energize the start coil, and you energize the timer here. So this will close to hold it, right? So we're holding. So S, bam, bam, bam and bam, and all the S's are going to close. So now you have a transformer that take the 480 from this side, 480 volt, it will dump it down. I'm going to transfer it to 240 volt here, right? They're going to a transformer. I don't know if you guys can see that. I'm going to take one phase going right here through the transformer, and it's going to go all the way through the motor. So see where you're getting one part of it. You're transforming the voltage. Who cares? We're reducing the voltage. When I reduce the voltage, here's my I start is going to go down. So if I have 100 amp I start, now it cuts it into, say, 30 amps or 40 amps. Who cares? No mechanical or electrical stress. So momentarily, the next thing that's happening is we have a timer. When this timer times out, this will close. Then the run will energize. So bam, bam, bam. So when this closes, I don't know if you guys can see. Let's take the same phase here. Track my phase here. You're going to come here, and you're going to dump the voltage directly. Can you guys see there's no transformer now for the path? We bypass the transformer. So when 480 comes in here, guess what's going to come here? 480. Now my motor comes up to speed. How long will you allow the motor to run at 240? Up to 10 seconds. What happens if you allow it to run at 240 higher than 10 seconds? You start smelling a nasty smell. Then you start seeing the smoke. Then if that's not an indication that something wrong, then a big ball of fire comes out of the motor. Then the circuit breaker will trip. If you allow it to sit at 240, you reduce the voltage momentarily. Any question, guys, about this? These are the same thing. One of them reduce it with a resistor, and one of reduce the voltage. They call it controlling the inrush by reducing the voltage. You reduce the voltage, you reduce the current momentarily for only 10 seconds. After 10 seconds, you bring the voltage back to 480 because I need the full capability of this motor. And I don't want to smoke it. Any questions about this? So that's really the controller. This just talks about in certain machine, the punch presses. There's certain machines, guys, they use. This is kind of a hybrid. They call it wound rotor induction motor. Wound rotor induction motor. It's almost like a synchronous motor. You're going to see it in a second. We have one. Did you guys wire the one that we have in the app? You didn't do it probably. Wound rotor induction motor. The nice thing about them, you can control the air rush really good on them, and you can control speed. So in this machine, two machines, Amman machine, Minnesota, they're using actually wound rotor motors in these. They rotate as magnetic field. So I don't know if they have what they do really they're not coming, but what they do is here's my motor here, and here's my stator, my rotor inside, and then you have the phase A, phase B, phase C. This is A, B, C, and then the rotor itself has wires, guys, that comes out of it, and they go to contacts, and they have resistors, bank of resistors. So the rotor itself has wires. I'm not going to spend too much time on it, but they have wires. Who cares? You can control the speed and the inrush on it better than the induction motor. Okay, so that's your secondary resistor, and we'll talk about, guys, the secondary resistor, how they control it. I have a nice pictures later on. You'll look at it. So it's reducing the speed and the inrush. Okay, any question, guys? So if I ask you one little thing, what's your motor of choice? Induction motor. How to control the inrush of an induction motor? In this day and age, you say VFD or soft start. In the old days, resistor, primary resistor, or transistor or transformer for induction motors. Okay. The second thing that you guys talk about here in the presentation is the direction of rotation. Direction of rotation is very, very important. You guys know that, imagine a machine that's the conveyor is supposed to go this way, and if you flip the phases, now it's going the other direction. Bad news, unless you want it to go both ways. Imagine a fan that's supposed to blow the air out. You rotate it, now blowing the air in. Now it's pumping the smoke out of the area. Now it's bringing the air and the smoke in. So rotation, I'm not going to convince you, rotation of a motor is a big deal. So they have, smarter than Chad, have a phase rotation indicator. The phase rotation indicator, guys, right here. First of all, you zero it. You put it on zero before you do anything else. Then the motor is de-energized. I don't know how you do this in bigger motors, guys. I really don't. In a smaller motors, you go to the rotor, Chris, right here, and you physically, mechanically rotate the rotor. So I want this rotor to go counterclockwise, right here. I want this motor to go counterclockwise. So if I physically grab the rotor and rotate it counterclockwise this way, this indicator either will say correct or incorrect. There's two. If it says correct, right, then you label these phases as their son, A, B, and C, if they say correct. If they say incorrect, then you go flip this one here and flip that one here, right? Flip these two. And then rotate it again. It should say correct this time. And then you label this will be a B, and this line, if I flip them, this will be then a B, this is an A, and this is C. And that's how you identify ABC in a motor. Who cares? The question always, who cares? If you change two phases on any three-phase motor, guys, you will change the rotation of that motor. Clockwise, counterclockwise. Big deal. So the phase indicator, the first thing you need to do, as I said, zero it, then tie them any way, shape, or form. Rotate if it's clockwise or counterclockwise. If it gives you a correct indication, you're done. If it doesn't give you a correct indication, go take any two leads, flip them. So make the AB and the BC, or the AB or the AB and the BA. Rotate again. It should give you correct, and relabel your system. Now the question, who cares? You would be a project manager walking, guys, into a plant, and they want to add a system, a motor or something, and you have to verify. Ask them a method. How do you verify the rotation of the motors? So that's a big deal, to verify the rotation of a motor with the phase rotation. Any question, guys, about this, Chris?
Yeah, you had said that lowering the voltage decreases the current, yet the formula for that, lowering the voltage would increase the current.
Which is why it would cook, right? And smoke.
I don't think you can have it both ways, can you?
The formula that we had, lowering the voltage will
Increase the current.
Yes.
So by lowering the voltage, if you're trying to, the starter, you just got done telling us using the starter,
Yeah.
you put resistors in, lowering the voltage, and now you've just increased the current.
Oh boy, big this. I equal V over Z. And I know that confusing. I know the formula that I told you is a confusing one. The formula that I told you.
The horsepower as well.
Here's how I know it's good. Here's how I explain it to myself.
Okay.
The voltage that I showed you, the first one, that's just lowering it within 10% of the nominal value. The one that I showed you. You lower it within 10% of the nominal value. So 480 plus or minus 10%, that will get you higher or lower amps. If you lower it substantially, as in cutting it by half, 1/3, like we do with the start, it actually cuts the current down. That's how I explain it to myself. It's based on the Ohm's law, right? Here's Ohm's law.
Yeah.
What happens if the voltage goes down here? The current will go down.
Yes.
That's the principle of starting the motor. The principle that we just showed, the formula that we showed, is really fluctuating of the voltage, not substantially cutting it by half or 1/3. That's how I understand it. Good point, though. Okay, the other thing, guys, I'm not going to go through how to identify. This is when you wire. You guys went with this with Gary. This is how you identify a three-phase motor. Here's what I want you to understand. Three-phase motors, almost all three-phase motors come this way, a Y. Come with 9 leads. They call them 9 leads. All of them come with 9 leads in a Y. Some motors come delta, but most of motors come this way. Now, if it's a Y, to identify them, if they're not identified, you guys went through this process of going from clockwise, from the top to the bottom, and going in circle them. And I'm not going to repeat this one. Here's 1, here's 2, 3, you go to the second 4, you go to the 5, you go to 6, 7, 8, 9. So these are all the leads. Who cares? Because almost all induction motors, you can connect them in 2 voltages. If it's 240 or 480, almost double the voltage. So they call them dual voltage induction motors. To make it easy to bring these motors, guys, in different systems, because we have different voltages, they make them dual voltage. They always rate them 230, 460, for example. So a motor like this could be rated 230 slash, what did they say, 460, 460. So I can hook it up high voltage or low voltage. And I'm not going to get into the whole details. Same thing for the delta. Can I get you guys to understand that 90% of what you're going to be seeing is a Y? Because Y, the current in a Y is smaller than the current in a delta, in the winding itself. But 90% of what you're looking is going to be a delta motor, a Y motor. But you can do it in a delta, and here's the configuration for the delta, and I'll let you guys configure that one. Any comments about this? Dual voltage motors comes with 9 leads, mostly Y. That's all what you're going to remember. You can tie them in parallel to get you high voltage, in series to get you high voltage, or in parallel to get you low voltage. And I'll show you a couple of systems. Any question, guys, about this? So these are my understanding. I like percentages, so I'm going to throw 10% of the time you have a delta motor. Delta motor, high air rush, high torque, you can get out of them. But the current inside the winding is high. That's why if you put a delta, the current that goes through the delta is going to be high, guys. So meaning, who cares if the current inside the coil is high? The coil is going to be big to handle the current, right? Any question, guys, about this? Delta Y, dual voltages, 9 leads. Both of them come with 9 leads. And this is how we identify the leads if they're not there. You're not an electrician, so most likely when you go to the place, it's going to be up and running. Single phase, I don't want to talk too much about single phase. Same thing, guys. They all come with dual voltages for single phase. They can get you high voltage. Can you guys write yourself? High voltage always goes with series. You put the coils in series. And low voltage always goes with the word parallel. If you understand this one, you would never go loose in transformers. The same thing. 120 coil, 120 coil. If I tie them in series, what do you get from the end? 240, high voltage. 120 coil, 120 coil. If I put them in parallel, like this, what do you get? 120, low voltage. That's the principle of operation of high voltage, low voltage, single phase, or 3-phase motors. These are the identification, guys, for single phase motor. I don't want to even mess with them. Remember that we did, so that they go by T1, T1, T4, T5, T8. This is the starting coil, the running coil, starting coil here, and running coil or coils here. How do you reverse a single phase motor? Who cares? Can you guys see how they flip the T5 and T8? Can you see how they flip the T5 and T8 relative to T1, T4? And to get you clockwise and counterclockwise. Okay. Any question, guys, before we move into the DC motors? And I'll give you a break in a second. DC motors, the most important thing about DC motor, guys, they used to be, Chris, help me here. They used to be superior, guys, because of one little thing. You run these babies on DC. When you guys have a DC system, is there a frequency for that? What's the frequency for the DC? There's no frequency for the DC. So if you reduce the voltage, you don't have to worry about the frequency. So easy to control the speed, relatively easy. If you want the motor to run at certain speed, you just tweak the voltage down. So that's the way it became very superior. So I have a 480 motor, can give me, let's say, I'm just going to throw these out of the blue. Okay, so I have a 480 voltage, and this baby is going to give me 1800. Let's just say 1800 RPM. If I tweak this one to 240, now I get 900 RPM. If I tweak this to 120, now I got 450 RPM. And if you keep going, you can control by controlling the voltage, reducing the voltage. So if you put the resistor in line and you just tweak the voltage down, increase the resistor, you increase the voltage or decrease the voltage, and then you get lower speed. That's where they were superior. Their problem, though, is their high maintenance. I'm recording here, otherwise they'll say like whom, but They're high maintenance. A lot of maintenance have to do on the brushes. They have a lot of brushes, guys, that imagine having a brush tied to a rotating object. And that, like a fan rotating, and there's a brush tied to it all the time. What's going to happen over time when things are rubbing against each other day in, day out, for hours? They're gonna malfunction. So high maintenance, a lot of maintenance involved in maintaining that system. So that's really the disadvantage of them, is very high maintenance. You have to change the brushes. You have to go clean the stuff over here, and so the high maintenance, big deal. This is how they simplify them. If you guys, the way they do them, unlike induction motors, you see that coil over here, they bring the powers directly to the rotating object. So they bring a wire to the coil. So the coil is rotating, guys, and they put brushes right into the shaft, basically, some part of the shaft. So you have the brushes that tie right directly to the shaft. So they wire the shaft. Here's how it looks like. I don't know if you guys can see that. So, and they have different configuration. You have the shunt field. There's the field windings and the series windings. If you want these babies to go, so they call it shunt. This is short shunt and long shunt. Now, who cares? The question, who cares? Who cares about short or long shunt? We do it a lot with the electrician guys. The way you wire it can give the motor high speed, high torque. So different configuration, the compound configuration give you better torque out of that motor. So they reconnect them, the coils. You're looking at coils, and all these coils that we're looking at are right here, guys. The coils over here, the field coils, they connect them in the following ways. You can have the series field exactly like short shunt, long shunt, and you can go ahead and read about the whole description. But it does one little thing. It gives you high or lower torque out of these motors. But ultimately, you're bringing one voltage. Can you guys see that? You're bringing one voltage to these babies? One DC voltage. One DC voltage. Then they have a compound. Look how they do them in the compound. It just really, the difference is how you wire these coils together, in series or in parallel. So you have the differential, what they call it, differential compound and cumulative compound. What's the difference? In the ability to get you more torque, less inrush current, and so forth. This is how they come, label them, guys. So the windings, the wire that coming directly to the brushes here, to the brushes, they call them A1 and A2. Then this is the series, S1 and S2, S4 series, and F is for the field. And you have commutating field. If you have another field for the commutators, they call it C1 and C2, or S1, S3, or S4. So it's like another series coil. This is typical. Remember how the motors are labeled in T1, T2, 3, 4, 5, all the way to 9? If it's a DC motor, they label them with A's and S's and F's. Who cares? These are S's and F's. Here's how I'm going to wire them. If it's a series, what is it? You tie these together. You bring this one here. Grab one of these wiring methods that we're going to do series. Let's do the shunt cumulative. So, and then you grab where's my shunt here? You grab this one, you tie it here, and you grab this one, right? You tie it right here, and then you bring the voltage from these two sides. So that's why they get you the whole wiring methods for these. This is one wiring method for that baby. Right? It's shunt across both of them, yep. So I grabbed that one and shunted it across both of them. Okay. Any question, guys? Any comments? Any question about these? If you're an electrician, we'll go through the details, blah, 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 but you guys are designers, just be aware of them. How do you change the speed of the direction of rotation? Direction, can you guys see how A1, A2 connected here? This will get you counterclockwise if you put the A2 here and the A1 here. So you flip these. Can you guys see how they flip them? How do you flip them? You take the wire that's supposed to come here, grab it, put it here. And you take the wire that's supposed to go here, flip it, and tie it there. It's really not. Flip the wires. And that will get you a clockwise and counterclockwise rotation. Any comments, any questions? Comments, questions? So that's your motor. Here's another way of, guys, another way I can't emphasize here is that A went to A1, went to A2, and A2 went to A1 to get you the same thing, counterclockwise rotation. For shunt motor, you just flip the A1 and A2 relative to the field. Relative to the field. Same thing here. The only thing you need to remember is just flipping, really flipping these relative to how they are connected. You don't mess with anything else, compound, whatever, as long as you flip the two, the A and A1 and A2. I know this one is going to be in the test, guys. How do you reverse a three-phase motor? Always just say reverse A1 and A2. A1 and A2. Huh? Yeah, that's it. See how A1 goes to A2 here, and A2 goes to A1 here, right? So technically, I don't know if you guys wiring wise, all what you're doing is you're taking that big wire, fat wire, and tying it here, and you're taking that big fat wire from here and tying it here. That's what really you're doing, is just tying the wire on the other side. So flip them. Okay. Should we have 5 minutes break, guys, and we'll continue with that one? Okay. Because of the DC motors, Chris, and everybody else, we need to have DC voltage. The only way, since Mr. Edison created the DC, the only way now we can get DC, substantial amount of DC, not the batteries, substantial amount of DC, is by converting AC to DC, right, Chris? That's the only substantial way, substantial amount of power that you can, like 50 horsepower, 100 horsepower worth of power, you can get in a DC format, is taking it from the AC and converting it. Guys, I don't know if you know by now. If you don't, please remember that. AC single phase, AC three phase, and DC are three different vehicles to carry the same amount of current. Like William, my friend, you came today driving, you drove your car. So, but it's the same outcome as you drove your car and you came to Dunwoody. That's the DC. If you drove a bus and you came to Dunwoody, you yourself drove the bus, came to Dunwoody, that's an AC. AC three phase. But the outcome is still you coming to Dunwoody. See that? The same amount of power. Or if you have an airplane, and if you flew an airplane to Dunwoody, that will be equivalent, say, to single phase AC. Still the same outcome. Everybody understand that it's a way of delivering electrical power to equipment. It could be DC, AC, or single phase, or three phase, or two phase. Cool? Can I get people to understand that one? This is the most. So I can have a 10 megawatt, transmit them DC or AC at different voltage and different frequencies. It's still 10 megawatt. Okay, to do this, guys, because we need to power a couple of things now with DC, especially DC motors. You don't have batteries for the most part. You have AC, so you need to convert. Long story, convert. You guys know the half-wave rectification, where it rectifies an AC, a beautiful AC, and it takes it into a one bulb, and that will go a bulb like this, right? Just one bulb. That's a half-wave rectification. We have full-wave rectification, single phase. With they do diodes. They forward and reverse the diode by flipping the voltages across the diode. They allow the diode, is like a valve, to make the current go if it's positive, or plug it if it's negative, and keep flipping the voltages across it. So that's how we get your AC. The outcome when they do the rectification is always a DC. The whole outcome that you want to do is always you want to find a DC voltage. I waited for you guys. They told me that you went hee-hee-hawing around.
He's turned around and sounded pretty quick.
Yeah, it's beautiful, huh? Okay. The second way, guys, is a full way rectification, single phase. The best way to do it is full way rectification, single phase, is what you're looking at right here, guys. We're rectifying AC to DC to dump it across a computer. All these machines are running DCs. That's how they do them. In our case, we're running it at machines. So what they do is they put two diodes, where if the signal is in the positive, it charges one way. If the negative, when you get this signal, when you get it to the bottom, it flips the polarity and flip it to the other way. So it gives you some type, it's not really an AC, but some type of a DC, So that's the whole idea. Can you guys see now? This is not really a DC, but this is definitely more, this one is more DC than this one, right? So that's the whole idea of getting you from a full wave rectification. These are the single phase. In three-phase system, guys, we use a bigger. But the outcome is, here's my, let's say, DC motor. If I have a DC motor, this is how we tie your DC motor, guys. You put the AC, I'm just going to say 240 here, and I don't want to do the calculation, so I'm going to end up 200 volt DC. You convert it to 200 volt DC, single phase AC, 200 volt DC, and you burn a DC motor. And again, I'm just throwing these numbers. Any question, guys, about the single phase full conversion with having, you can either have a transformer here, isolation transformer, or you can have the bridge, so-called bridge. And today is not the day of talking about the diodes biasing and so forth. To calculate, so take this first. You take an RMS value. Let's do example for 480. I have a 480 RMS value that I need to convert to a DC. The first thing you multiply it, the first thing you do is you multiply it by this number. Can you, Chris, help me with this, please? 1.414. So you multiply it by square root of 3 to find the peak.
Square root of 2.
Yeah, I'm sorry, square root of 2 to find the peak. What would that be here? This is to convert AC voltage into DC value-wise.
678.
678 volt. Cool. Then you take this 678 and you multiply by this magic number for the average value. This is the average DC value. What would that give you, Chris? 0.637 of this number. That's for the full wave rectification. 432 volt. 432 volt. If it's single half wave, which you don't usually use, if it's half wave, you divide this number by 2. So what do? Divide by 2, that will give you 2, press 2 what? 260. 260. Okay, so long story short, most likely full wave. So you took a 480 and you convert it down to 432 volt DC. Can you guys see what we're doing? We took just value-wise, here's my AC voltage, 480, and I convert it into almost pure DC. This is my 480, and this is 432, 32 volt. So there's some losses in the voltage, right? The vehicle is still the same. You deliver the amount of power at different voltages, Any question, guys, about this? That's how kind of try to get an idea when you convert from one AC voltage, what's the outcome in the DC voltage? Not one-to-one. There's some monkeying around to get you the actual average value.
But don't we care about the current?
Yes. Yes. The current is a function of the load, though. If I know that my voltage DC is 430 now, how much current depends on how much load you have. So if you put here, that's a good point. So I know my voltage is 432 now, and I want to tie 10 kW on it, right? So you take the 10 kW and divide it by 432, and that will get you the current. It's a function of the load. The current is a function of the load. Does that make sense, guys? The current is a function of the load that's coming.
There's a constant of 637.
I don't know. That's the statistical value to get you the average from the peak. The average signal, a sinusoidal signal, mathematically, to get an average from a peak is you multiply by this number. Okay, now the superior full conversion, guys, as you know, is three-phase. So I have my phase A, my phase B, my phase C, put it in a bridge like this one, and you convert it a three-phase into DC, into this is a 100 horsepower DC motor. Can you guys see that? 100 horsepower DC motor coming from the voltage here, let's just say 480 volt. Chris, we came up with voltage for, 432 volt. Let's just say for the 32, assuming it's right. So I converted and I'm running 100 horsepower at 432 or whatever the voltage is. I don't know if you guys can see it. This is, believe it or not, it's kind of an AC. I don't know if you can see with little ripples here. Right? Here's where the DC is. Everybody can see, guys, that DC at the top here? The AC though, the AC was going 3 signals here. We have 3 signals going AC here. Each one of these signals, when they come, they convert. And I don't know where's the other signal, Chad. Where's the tracking it here? Okay, whatever. So these 3 signals, 3 phase, converted to 1 signal DC. All this junk at the bottom, done. There's nothing here. What you see is that red thing, little DC ripples at the top of it. So long story short, that's your DC conversion. Okay. The way they do them, guys, they have here's the whole idea is to get you 100 horsepower motor here, speed control, to get you a speed control in 100 horsepower motor. So here's a DC motor. Look at that DC motor wired from a 480 system AC through a DC drive. I have a DC drive, convert the AC to DC, and I have a controller. I don't know if you guys can see all these controllers to tweak the voltage, and I'm running it across 100 horsepower. So long story short, guys, that's if you have a DC motor right now. In order to run the DC motor from an AC system, here's what you want. You want the following. Here's the one-line diagram. It's going to look something like this and something like this. So here's my 100 horsepower. This is DC drive, they call it. And this is my, I don't know, this is 100 horsepower. Let's say that's 300 amp. And this is my 480 system. See what you do? Here's your DC motor, tied to a DC drive and connected to an AC system. Can I get you guys to understand how you tie a DC motor to an AC system through a DC drive? Can I have a thumbs up, Chad? That's very important to understand that. You get a DC motor tied to an AC system via a drive. That's what you're looking at right now. They call it DC drive. What's a DC drive? Taking the AC, converting it to DC, dumping it across the DC motor, and in the process, what do you do though? You control the voltage. So if you want the speed to go, I don't know, let's just say this was let's just say for practical reasons 400 volt. If I want this motor to run, this will give me 1800 RPM. If I reduce this one to 200 volt, I can get 900 RPM. Who cares, Chad? Great speed control. Great speed control. Any question? So can I buy a DC motor and install it in the building that you have, Chris, that we're building right now? No problem, Chad. How am I going to install it? You're going to buy a DC drive and tie it to it. Cool? Okay, so that's what you're going to hear at DC drive. Now, the next step, guys, is VFDs. You're going to hear about the VFDs. We specify VFDs. So the DC drive, when you see a DC drive, Cutler hammer, guys, DC drive goes with DC motor. Now AC drives goes with AC motors. So I have an induction motor and I want to have an AC drive, which is a VFD, and speed control it through a VFD. So that's the DC. When you have an AC drive, you're controlling basically with less maintenance on the DC motor and so forth. You're controlling, the most important thing is we are controlling the speed of an induction motor with VFD. So DC drive goes with DC motor. DC motor is high maintenance, out the window, except for certain application. Most of what you're going to have in the air handling unit right now is induction motor. With induction motor comes a VFD. What is a VFD? VFD takes the AC to DC, control the DC, then spit the DC as some form of an AC across the motor. And in between, guys, when we get the DC, you can reduce the voltage, and then invert it at the right frequency and at the right voltage to control the speed.
But it is outputting an AC.
Some form of an AC pulsation. It's an AC. The output is an AC. Yeah, it's alternating some form of a pulsation alternating AC. You're going to see pulse. You'll see there's a nice picture of it in a second here. So to control the speed of a motor, guys, we can change the poles. That's the old-fashioned way of controlling the speed. The new-fashioned way right now is controlling the frequency and the voltage. The frequency and the voltage. Okay. So we have the induction reactance. So what this says, guys, in an AC motor, take this. Here's voltage. Here's frequency. I have 480 volt and I have 60 hertz. If my motor, Chris, runs at 480, 60 hertz, out of this outcome, I can get, let's just synchronous speed, 1800 RPM, 1800 RPM, 1800 RPM, okay? If I reduce the voltage to 240, I have to cut the frequency by half, well, for the most part. So that will give me 60 hertz. That's how they control a speed of an induction motor. See how they cut the voltage down, cut the frequency down. This will result with what? With 900 RPM. Now the only thing, Chris, that DC does the same thing. The only thing that DC doesn't do is it doesn't care about the frequency because there is no frequency. So when they discovered electronically, they can alter the frequency, guys. They can change the frequency. The whole DC motors they were superior in terms of speed control. They become obsolete. So you can have any motor right now, put an AC drive on it, VFD, and you can speed control that motor. If you can speed control a motor, is a big deal, guys, in the industry. Can I get you to understand speed control an air handling unit or a chiller or a rooftop unit is speed control? It means you can control the temperature in a room. It's very specific control. It's not just either hot or cold or in between. No, you can make it as hot or as cold as you want it, for the most part. Anyway, the idea, guys, by controlling the frequency, because the impedance, remember the impedance of a coil is proportional to the frequency. The impedance of a coil, XL, is proportional to frequency. So if the frequency goes up, the impedance goes up. If the frequency goes down, the impedance goes down. So if you cut the frequency down, the current will go down. In order to reduce burning the equipment, guys, you reduce the voltage proportionally to the frequency, and that will get your speed control. So we reduce the voltage proportionally to the frequency. The smarter than you speed, friend Chad, they do it this way. I want you guys to take, here's a 480 volt system. Convert into, let's just say, 460 volt DC and spit it out at 480 volt. Can you see it? So this is where the speed control. First, they converted to DC. Now we went from AC, which we care less. We went to DC. That's where we do the speed control. And then we spit it back into AC because we need to tie it to an AC motor. Can you guys see the process in between? So you have to go through the stage of DC so you can speed control the voltage. Then with these diodes, you can they cut the frequency to recreate the AC, recreate an AC from a DC. So they use the variable frequency. They use, guys, the SCRs as methods of conversion, as you can see here. The problem with this process, remember that I talked about harmonics? What's the problem with harmonics? Overheat transformers and motors, blow up fuses, and circuit breakers opening. So there's a few problems when you go through the process. There's different technologies, guys. The other technology that they use is IGBTs. The IGBTs will have advantage for them as they're better in terms of frequency than the others. No spikes. There's certain spike, guys, that comes out of these. Spikes, everybody knows what a spike is. A spike is a very short amount of time, very high voltage. Just spikes into it. Because of the whole conversion system in the transistor, you get spikes. Who cares? You could burn equipment. All this, guys, happened with the manufacturers. I'm going to directly, so we have IGBTs as a technology. All what you care about right now is buying an AC VFD that control it. How does it do that magic? AC, DC, control DC, spit it back at the right frequency and voltage. When you put a VFD, so here's my motor here, here's my VFD, here's my motor, here's my system. Your VFD, guys, in order to drive a motor, and these are induction motor, with a VFDs, guys, run the speed control the motor. So first of all, you can ramp up the motor, ramp it down, so less stress, mechanical and electrical stress in the system, and speed control it. In order to do that, guys, you need to do the following. First of all, in some of them, they use separate blower to cool the motor. They need to be able to cool that machine. This baby has, so you have a different blower to cool it. They use more insulation paper between the windings. So they create what they call an inverter motor. So when you read at Michelle Cooley, if you read the mechanical spec and the electrical spec, they always specify inverter rated motor. Not any motor. They want a motor that's specifically designed to run with inverter. Now, can I run another motor? It's induction motor, but it's designed more robust, more strong, can handle the heat. And here's a description of it. They have separate cooling system, so it doesn't burn prematurely. Because you abuse the motor when you speed control them. So they have phase paper, guys, between the phases. They have paper separation between the leads. Magnetic wire is in the winding is higher rated insulation on it, and they are fatter and fluffier motors. I can get you guys to understand one thing. If you have an air handling unit with a motor, you're going to find a specified inverter rated motor. Who cares when you read it? What do they mean by inverter rated motor? They mean specifically designed motor to run with VFDs. Who cares? It wouldn't die prematurely on you. It can handle the stress that's coming out of reducing the frequency and the voltage. Reducing frequency and voltage, guys, create heat. Still speed control, but create heat. So we need these motors to be able to handle the heat. That's all.
Chad, how long have VFDs been around?
Oh boy.
Okay, so they've been around.
10 years, if not more. At least 10 years, if not more. Probably maybe 20. At least I've been involved in them 10 years. Yeah, the technology keeps going better and better on them. So these are, please remember, the inverter motor. This is just one way of the CSRs, guys, flipping the voltage and getting you the AC. The last thing I want to talk about, guys, is when you have a VFD, without getting into the low speed, low torque, you can set your, now VFD setting, VFD. When you set your VFD, guys, you need to put the higher current limit. What's your highest limit? Say, I want to see 100 amp. Okay, what is voltage per hertz? What is voltage per hertz ratio? I'm going to use a 1-to-1 ratio. So 1-to-1 ratio. What's your maximum frequency? I'm going to use a maximum frequency of 60 hertz. And what's my minimum frequency? Minimum frequency, how low you want the motor to run, how fast you want the motor to run. I want to put 20 hertz here. So these are translate to RPM max, and this is RPM mini. So these are the things, guys, when you drive the VFDs. We don't have VFDs in this room. When you drive them, you have to go there and adjust and set these limits. So I can't go higher than 100 amp. The voltage is going to go 1-to-1. So if the voltage is 480, the 60 hertz. The voltage 240, 30 hertz. So you reduce the frequency. Frequency, guys, also do the acceleration and deceleration of the ramping up. When you have the nice thing about them, here's my motor. I ramp up my motor to full speed, and when it's done, I ramp it down. So this is say 1800 RPM. This is synchronous speed, and this is 0 speed, and this is 0 speed. 0 RPM, R, P, and up. Everybody knows what accelerating the motor, bringing it slowly, gently to speed. Who cares? No air rush, no stress, electrical stress, no mechanical stress. And when it's up and running now, if you turn it off immediately, you know what's going to happen? The voltage goes way up because a huge motor comes up, and you turn it off. There's a huge energy has been consumed. The voltage pumps up when you turn the motor off. So what they do, the smarter that Chad discovered, instead of just turning it immediately off, how about if we give it 10 seconds to turn off in 10 seconds instead of instantly? So they ramp it down, they reduce the voltage slowly, slowly, slowly. So slowly the motor comes to an end.
So is the voltage coming from, is it the voltage kicking back from the motor? Or
No, this is all through the drive. All this is controlling the drive. When you push the button to turn the motor off, inside the drive says now we have to start the sequence of turning off. So it starts reducing the voltage slowly within 10 seconds. And at the same time, the speed of the motor goes slower, slower, slower. Within 10 seconds, it comes to 0 voltage, 0 speed. Versus you push the button off and it cuts the voltage immediately. So it takes 10 seconds to kind of ramp it down. All this, guys, will make smoother, better operation for equipment. That's really the whole idea. Okay, so I wanted to show you a couple of pictures here, guys, and then I will wrap up here.
so Chad, for
Go ahead.
VFDs, would they have to be located close to the mechanical equipment on the roof, or can they be in an electrical room and then
Close to the equipment. The best location for VFD is close to the equipment. If you can't, they do kickbacks of harmonics and so forth. So the best location for them is right next to the equipment. If you can't or will not, then they put filters way at the end. Location right next to the equipment, the best location for them. Otherwise, they will create some harmonic issues, but they have a filter. They have filtering issues that they can deal with it. Okay, so I went through this one, guys. The control. Here's how they do the old-fashioned way. This is Chris's in the 60s, how they used to do them here. Oops, sorry there, but they used to have 2 sets of windings, guys, and based on connecting which set of winding, they can get you different speeds. Can you guys see that these are speeds that they can get forward or reverse? That's the old fashion of reversing and forwarding a motor. And the new fashion right now is what? VFD can reverse it, forward it, and speed control it. So just be aware of that one. So that I'm going to emphasize that one. We talked about these guys reducing the voltage. Here's Chris. Here's a wound rotor motor. Can you guys see a wound rotor motor where they can have actually conductors coming out of the rotor? So who cares about this baby? They can speed control it. What they do, I don't know if you guys can see, they can, by closing these contacts here, they can run this baby at 3 speeds, I believe, right? They can have low speed, second speed, and third speed. And you know how they do it, Chris? They close this contact, bam, bam, here's get you 1 speed. They close these contacts, bam, bam, another speed. And they keep them open, give you a third speed. So if you have a wound rotor motor, this is called wound rotor motor. They control, it's nice because you can control the speed, but what's the problem is, the rotor has windings. Can you guys see the windings of the rotor and the windings of the stator? So with the advantage of VFDs right now, VFDs have made induction motors more superior. Here's how they control, guys, the wound rotor motors. Here's a controller that can get you 3 speeds by very easily closing these contacts and opening some and closing some through this control system that I'm not going to walk you through. Any comments, guys? Wow, if you hear wound rotor motor, old fashion of speed control. That's all what you want to remember. We talked about, guys, phase rotation. Phase rotation. So you so the phase rotation, the first 2 things for phase rotation. We talked about how to get the phase rotation for the motor, guys. So let's just say we want it to go this way, and it gave us an indication. See how they're tying it to the motor? So this is phase A, this is phase B, this is phase C, right? Now I need to tie it to the system. This is the power system. Power. And I have no idea what is phase A, what is phase B, what is phase C. No idea on the system. So first you identify the rotation that you want. So identify phase A, B, and C like we did. Then look at the step 2 that they do. Then you go to the then you go to the line. You tie it to the line. Now you, by tying it to the line, guys, this indicator here, this indicator here, either give you, it's at the 0, either give you correct or incorrect. If it gives you an incorrect, Chris, you know what they do? They grab this and tie it here, and this, tie it back here, and then turn the flip the switch again. And it gives, if it gives you correct, then this will be, because I flipped them, this will be C, this will be A, right? And this will be B, because I flipped them. So who cares? The phase rotation can identify the phases of the motor, and they also can identify the phases of the system. If you don't know what the phase is, by code, guys, the phases in the system have to be identified by label. They have to label. But if they're not identified, then you can also identify by the phase rotation. Here's another example, Chris. Suppose that you have doing maintenance and existing building, you need to identify which one is phase A, phase B, to tie it to a temporary wiring. Come in, guys. I want to take down the switch gear. I have a temporary switch gear in the parking lot. I need to cable the switch gear in the parking lot into my building, right? So the first thing you need to do is you tie it to the existing and flip the switch on. Okay, now if the indicator indicates correct, let's just say correct here, then you go label this one phase A, right? Phase B, phase C. If it's say incorrect, guess what you're going to be doing? You're going to go flipping any two phases, and correct, it becomes B, A, or C. Okay, so here's the first thing. The second one you're going to do, Chris, is you're going to grab this one here, and grab this one here, and this one, put it right here. After you take them from here, take them the other side, and energize again. If this guy indicates correct, then this phase is A, B, and C. Otherwise, you have to reconnect them, and it might be C, B, and A. Does that make sense? Identifying the rotation of two surfaces. If you guys tie the second surface before you identify the phase rotation, all your machines inside the building will be going backward, reverse. Some machines, guys, have reverse. They have protection from that particular thing. If they see the rotation wrong, they'll trip you alarm and so forth. So you can identify the rotation of the machine. Okay, here's identifying. We talked about all these configuration, guys. The only thing I want to tell you, Nick, if you put them here in parallel, can you guys see how the coils are in parallel now? That'll get you low voltage. If you put them in series, can you guys see how these coils are in series? If you put them in series, I'm sorry, the delta in parallel here, that's also low voltage. And this one will be, where's the series? If you put your coils in series, it's going to give you high voltage. If you put them in parallel, it's going to get you low voltage. I don't know why they don't have that. Oh, here. This one, for example, the two coils are in series, then we'll get you high voltage. Always series high voltage, parallel low voltage. I'll get into the. Here's a single phase motor. We talked about this one, guys, how you connect them. T1, 2, 3, 4, 5, 6. Different windings, different configuration. I'm going to go all the way to a couple of frequencies here. Here's the single one diode rectification or single rectification, dual rectification. I want to go one little thing here, Chris. Here's the output from a VFD, guys. Look at the output. It's not purely sinusoidal. It's almost square wave. Then with the IGBTs, it becomes very similar. This is the IGBT. This is what's coming out of your VFD. So it looks something similar to a sinusoidal wave. Something similar to the sinusoidal wave, but it's really not a sinusoidal wave. So the motor doesn't care. So you can speed control it and still cooking the stuff for you. Here's the pulsation that we talked about, how these, it looks like a out of the VFD, guys, it looks like an AC. The motor looks at it and see it as an AC, when in reality it's just very short pulsation that's giving it to the motor. That's how the system works. Um, Insulation. This is just a couple of pictures, guys. How they, if it's inverter motor, they do the stator cores and they have insulation papers between them. So long story short, inverter rated motors, better insulated. Talk about these conversion. There's a couple of things that we know. VFDs, a couple of VFDs. This is my favorite, Chris. This is what you do that, but I want to really indicate that one. If you have, let's take a 15 horsepower motor, and I want to take all these for the 15 horsepower motor, and all of it. So I want you guys to look at, if you have the efficiency at 1/2 load, and 3/4 load and full load. Then you guys see how the load, what happened to the efficiency as the load goes up? Improves. Efficiency goes up. The power factor, what happened to the power factor as the load goes up? Goes up. How? If I can get you to understand that mechanical equipment are more efficient and the power factor is better when they're fully loaded. That's what this is telling you. If you want a machine to run efficient, you have to run it at full load, not half load, not overload, not 3/4 load, full load. And if you run it at full load, the efficiency will be the best and the power factor will be the best. That's what this is indicating. Can I get you guys to say, Chad, we got that one? Full load for motors? If you can look at that. Okay, so that's machines and all this good stuff. Okay, any questions? Any questions? That's really what I want to go over.